Welcome back. Let's talk about assignment 6. Here I want you to implement a binary search tree using a node pointer implementation and then process it, that is print out all the nodes using a couple of different traversals and then draw a couple of pictures, right? So let's go through this. So first of all, here's the structure that I'd like you to use. So I'd like you to use a linked implementation for a tree. So you've got the data element, which is also called the key, and then I've got a pointer to the left and right nodes. So I want you to write an insert function. So that's going to be a brand new function you have to write. Then I want you to write a pre-order traversal and a post-order traversal and an in-order traversal. These three functions are just the same traverse function that's in the notes. They're the exact same functions, but if you notice in the notes, they're all called traverse. So that's going to cause a name conflict in your program, so you have to rename those functions. But they're the same exact functions that are in the class notes. It's just traverse. But the pre-order and the in-order and the post-order traversal or versions. Okay, then I want you to write a search function which looks for an element data in a tree and then just counts how many levels deep that was. Okay, so it basically returns the height or the depth of in the height of the data element, like how far down from the root in levels is this data element. Okay, and I want that to run in log-in time, which it should. Okay, well, we'll talk about that. All right, so then after you've written the insert sequence, then use this sequence and build a tree. And it's going to have a particular shape because the shape of the tree depends on the sequence that you use. And I covered that in the last video, so make sure you've watched that last video. Okay, then after you've got that working, call print order, pre-order, and post-order on this sequence, and you'll get a particular sequence of outputs for this particular tree. And then I'd like you to call search on this tree for a couple of different numbers and return their depth in the tree. And once you get that working, use this guy. Use this big old tree right here. This is a 100 element tree. The nodes are between 100 is the lowest value and 199 is the highest value. So there's 100 elements in this tree. So it's a 100 element tree. Then do some similar stuff. So what here? Some of this I said already. So search sequence A for values 1, 4, and 2. So it'll return the height of 1, which is going to be the first level, right? Because that's the first node in the tree. I mean, what's the tree going to look like? It's going to be 1, then 5 is bigger than 4, then 6 is bigger than, let's see, we start here for 7, and it's bigger, 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 and then 2 is bigger than 5, or bigger than 1, less than 5, less than 4, it's going to be 2, and then 3 is bigger than 1, less than 5, less than 4, bigger than 3. So when you search on 1, you should return the value 1. When you search on 5, you should return the value 2. When you search for 3, you should return the value 3 because it's level 3. And when you search on 6, it should return the value 3. Okay, and I'm asking you to search for 1, 4, and 2. So 2 should 1, 2, it's fourth level. Sorry, element 2 is fourth level. I'm asking you to search on 1, 4, and 2. All right, then do that for sequence B, your gigantical tree. And the number 42 will be somewhere down in the tree. Okay, do that. Then traverse the trees, traverse them and do the pre-order and in-order and post-order traversals. In-orders will come off. In-order is going to be 1, 5, 4, 2, and do these 3 traversals. And do that for both of these trees. And let's see. Then I want you to draw this, draw the sequence for A, and show this path, and show the X's coming off for each of the three traversals. And I think I used O's for the in order. Show those coming off, and the triangles for post order, show those coming off. Okay, so that's a little hand, a diagram thing you need to do by hand. Just do that for sequence A. Then tell me the time complexity of these functions that you're going to write in terms of n, the number of nodes. Okay, think about that and just tell me what those time complexities are. And that's pretty much it. Let's look at what you got to do. These code-wise, these guys here are the same traverse functions that are given in the notes. Insert, let's look at insert. That's going to be kind of the harder one to do. And search, once you've got insert working, I think you'll be able to figure out search. Yeah, well, to get search, you could either modify insert and get that working, or you could modify one of these pre-order traversal things and get that working. So look, the pre-order, the post-order, in-order traversal, that's just traverse from the book, and that's a recursive function, right? Traverse is just a recursive function as given in the notes. This guy here, I'm going to give you an iterative version. And both of these are going to, well, they're going to run in log n time. No, wait, no. This one's going to run in log n time because it's only going to go the height of the tree. And it's going to be iterative. These three guys are going to be, well, it's going to be n, right? I mean, it's traverse. What's going on with traverse? You're looking at every node n. So by definition, if you look at every node n, it's going to run in n time. There's nothing else you can do about it. It doesn't matter. That's all there is to say, is that if you look at every n, you're running in n time. Yeah, so, but still, you could, so I'm kind of giving you a hint about what search needs to run in. All right? But let's look at insert. This is posted. Trying to help you out here with what the code might look like without actually writing the code for you. So you're going to have a global root pointer. To do insert, you need to make a node and clean it up. Put the data in it. Set the left and right pointers to null. Okay, so you need this structure. You do this. Then if the root is null, which means there's an empty tree, then all you need to do is hook up the root to the new node and you're done. Okay, if the tree is not null, then you need to do two things. First, you need to find the insertion point. Then you need to hook up the new node. So let's look at finding the insertion point. And the way that I'm suggesting you do it is this way. You have a couple of pointers. They're like the root pointer, except they're local. You have what I'm calling a cursor C and a precursor P. Set it up in a loop. Initialize the loop such that C and P are thus. C is pointing to the root and P is pointing to, well, nothing. P is null at this point. But then you're going to loop C down by going moving C to C next. And what is C next? Well, it's either the left or the right, one of the two, depending on what the value in here is. Right? So you're going to move C down in a loop to the left or to the right, depending on the value in here, and P is going to follow right behind. P is going to lead, or follow, but kind of follow like a dog, right? It's behind C, but it kind of needs to move first. Otherwise, you're going to lose it. Right? Following like a dog, dog is on a leash. He's out ahead of you, but really he's following you. Okay, so code-wise, be careful that you do these operations in the correct order. Anyway, that's the loop. The loop just moves C down and P down. And then when you get to this condition, that is when the cursor is pointing to nothing, it means you found the insertion point at P. Right? Because you found a blank spot, and because C is pointing to nothing and P is pointing to the last node before nothing. All right, just to be clear, this thing could go on some crazy path down the tree, but at the end, P is going to be pointing to that, and C is going to be pointing to nothing. They're going to run down some branch going alternately left and right, or not alternately, but sometimes it'll go left, sometimes it'll go right, and when it stops, it'll look like this. And at that point, you need to hook the node up. So you just got to do a comparison of the data with the data that's in P here, and then hook up the new node either to the left or to the right of P. That's it. It's pretty simple. Here's a little note on messing around with the cursors. But anyway, to help you out a little further, refer back a couple of assignments to this thing, the linked list implementation. We've got a node structure, and there's a couple of functions in here that are similar to what you want to do. Traverse is similar, except you need some logic to decide whether you're moving left or right. Like here, when we traverse, we just go straight on down, but now we need to check, do we go left, do we go right? Okay, so it's very similar to what I did in traverse here. You want to look at that somewhere in here. Traverse is in here somewhere. Okay, that'll help you. What else will help you? I don't know, this is posted. I'm not sure if that's super useful, but that's up there. Let me check. Yeah, that's about it. So basically you have to write this insert function and then use that to build a couple of trees, and then get your traverse functions to print the trees out, and this is going to be a big long list, a lot of output for the big one, but print those guys out, and then do some search operations to find the locations of some elements in as far as their height in the tree. And then I'd like you to draw sequence A in the traversal diagram, with the path going around the tree. But just do that for A, not for B, right? That would take you, this would be pretty mean to ask you to draw a picture of this. Don't draw this. Don't draw this one, just draw this one. All right, so make sure you've watched the previous video where I go through a lot of the details in this, and then refer to some of the code you might have laying around that is very similar to this. All right, hope that was helpful. See you next time. Bye.